Hello, everyone. My name is Ethan Ortiz. My instructor was Dr. Piero, and my title of my Acre project is Adjusting Reactive Intermediate Lifetimes Through Steric Congestion. So you will be able to see some moving components in my presentation. These were just added for a little bit of fun, making chemistry a little more interesting to you guys. So here we go. Introduction to chemistry. So these are just a few terms and vocabulary words that I'll be using throughout my presentation. So a ligand is an ion or molecule attached to a metal atom by coordinate bonding. A catalyst is a substance that increases the rate of a chemical reaction without itself undergoing any permanent chemical change. A reactive intermediate is a short-lived, high energy and highly reactive molecule. And an NMR spectroscopy, or nuclear magnetic resonance spectroscopy, applies magnetic fields and radio waves to the nucleus of a molecule and collects data on the chemical environment of said molecule. So really quickly, I just want to teach you guys how to read line angle structures. I use these structures very much throughout my presentation, so I just want you to be able to read it. So as you can see on the left, there is a structure we call Lewis structures in chemistry. Lewis structures represent and show all atoms within a molecule. So as you can see in the structure, you can see all the carbon and hydrogen and non-carbon atoms being represented, plus their bonding pairs, lone pairs, and whatnot. And as you go down to the right, there's this simplified form of this structure, and these are called line angle structures. So where carbons once were before, you can see their vertices now, and the hydrogens that are connected to those carbons are now absent. So they're implicit. Whenever you see an endpoint or a vertice, you know that if there are not 4 bonds, that those remaining bonds will be replaced by hydrogen. And the only hydrogens that are represented are the ones attached to non-carbon atoms. So as you can see, this oxygen has a hydrogen bonded to it and is represented. So that any non-carbon hydrogens will be represented. So what did I want to accomplish in my Acre project? I wanted to create the ligand catalyst that Dr. Piero once theoretically created, and I want to form the synthesis of the molecule. So Dr. Piero has created the molecule as seen on the bottom right-hand corner, but my job was to create this top left-hand corner molecule or structure. It doesn't look that different. The only thing I was introducing was steric bulk. So as my starting point, I wanted to add 4 methyl groups. As you can see in blue, I want to add 4 methyl groups so I can study the tweaking of the reactivity of the molecule. And my project was really to hone in and study the reactivity of the molecule, as you can see for step 2. So as I introduced different types of steric bulk, I don't know what we could have added, but for the starters, it was these 4 methyl groups. If we would have continued, we could have studied different reactivity. And as a final step, I was to publish. I have not made it this far, actually, and you will see throughout my presentation why not. So as you can see, my entire ligand is above, but we can break this ligand down to synthetically make my ligand. I broke it down into 3 main pieces, and I spent a majority of my time, basically my entire Acre project, creating this bicyclic guanidine. So you can see on both sides of my molecule, there's these bicyclic guanidines. And this is when I spent a majority of my summer Acre doing. So above, you can see these set of chemical reactions. And this was my initial attempt or my initial reaction process in trying to create my bicyclic guanidine. This process, it might seem like 3 short reactions, but actually all reactions combined took about 5 days. And my starting materials for this reaction was ethylene thiourea, or a form of it, and some amine group. So this amine group was what I was really focusing on. And that would further down create my bicyclic guanidine. So this process was unsuccessful my first week, and I continued to try and tweak the conditions of this set of reactions. And I was really changing the times I set up for my chemical reaction. So like, let's say for example, my first reaction, this reaction lasted 24 hours. I would set my reaction up and test a sample of my end product at different timestamps to make sure that I was actually getting what I wanted. And what I wanted was this this end product. And I did, well, when that didn't work, I tried different solvents. I tried different ratios of starting materials just to see if I could find out if I was getting my bicyclic guanidine. And through testing, I used NMR spectroscopy. The NMR spectroscopy I took of my products, which I don't have represented spectra in this presentation, but I took a lot of them. So when that first initial method did not work, we changed up the method kind of entirely. As you can see, there are two methods here. Each method would have the same endpoint. Dr. Piero and Dr. Hammond actually came up with these methods. These were not found in the literature. Both of them combined their knowledge of inorganic and organic chemistry to find out a process that would work. So as you can see, each method starts off with this this large molecule. I had to create this starting material, and that's what this initial set of reactions above the two methods are. So in my new methods, I use this new molecule called a bacylation group. A bacylation group is a protective group. It does exactly what it sounds like. It protects my molecule, and it gives it a amount of reactivity that is beneficial, right? So each of these processes, I didn't get a lot of time to tweak them. I initially tried to start them from start to finish without tweaking anything. Everything was as it was kind of up in the air at the moment. Neither of these processes worked, and that's sad to say, but I kind of ended my project on this last attempt. Again, these processes, as you see, every one of these arrows, that's a reaction, and the end product is after the arrow. And some of these reactions could take up upwards of days. And to even see if I was getting my products, I had to test NMR spectroscopy. I tried different purification methods to see if I can make my samples purer, to see if I can move on to the next step. But sadly, it didn't work out that way. So theoretically, if I had created my bicyclic guanidine at any time within my Acre project, I would have moved on to one of near the final steps. So I would have taken my bicyclic guanidine and combined it with this, it looks like an aromatic ring with two bromines coming off of it, molecule. And I would have, it would have been one reaction to get this large crown-like complex. And really, this was nearing that would have been nearing the end of my need to create the complex. All I really would have had to do at the end of this was one more reaction, and that was to get my copper ion in the center of this crown complex. So some of the machines and equipment that I used throughout my time in my Acre were a rotovap. So rotovap is really just in this container or this basin. It's a hot liquid. It could be either water or another type of solvent that you would have different heating points or boiling points, and it would heat up a sample of whatever you got. Maybe this be your end product, maybe this be one of your starting materials. But usually when you want to get off some type of solvent within your sample, you would heat up this basin, right? And it would heat up your sample in turn, and the evaporated solvent coming off of your sample would go up this shaft and fall into this condenser. So this condenser, you see this coil of glass. Within this coil of glass, there was running cold water. So any solvent that evaporated off would be cooled down and then condensed back into a liquid, and that liquid fall into this waste round bottom flask. So this is what I use a lot to dry my materials and to actually get any solvent off my materials that I initially used before. NMR machine. So this machine is really just a huge magnet, and I would insert a small sample of my product and have it go down this large tube like a funnel, and my product would spin really fast within, and it would shoot a whole bunch of magnetic and radio waves into my sample, and the computer on the side would actually read my data that I was collecting into this spectra that was easy for me to comprehend. And then I used a syringe pump. A syringe pump, if I really, it's really convenient. Really, I just put my syringe on top of whatever I needed to be, whether it being a starting material or end product, and it would slowly administer over a certain period of time, depending on what rate I input in the keyboard. It would insert whatever I want into let's say an Erlenmeyer flask for a certain period of time. Like if I needed a reaction to go really, really slowly, I could set probably like 15 milliliters of dichloromethane for about 3 hours. And over that 3 hour period, 15 milliliters of dichloromethane would be administered to whatever reaction that was conducting. And then this glove box, it's this really big containment unit. So it's really just a man-made atmosphere. So as most people know, our atmosphere is made up of a whole combination of gases. And this some of the materials I was working with were highly explosive and could not be exposed to air. So this was a nitrogen-based atmosphere that was synthetically made, of course. And these little black holes that you see are actually big gloves. And within, I conducted a whole bunch of experiments. And to get those experiments in and out, there are these little chambers on the side you can see here. They change and vacuum out any air from the outside world, and then it allows you to go in between the nitrogen-based atmosphere and the atmosphere that we're used to outside. So I just want to give a thank you for Dr. Piero, the Acre program, Dr. Hammond, and the ACSPRF. I really had a lot of fun during my Acre, and I just want to thank everyone. Thank you.